Vector-valued functions and space curves. A vector-valued function is a function of the form RT equals FTI plus GTJ, or FTI plus GTJ plus HTK. Now keep in mind here, it's two-dimensional if I just have an F and a G. It's three-dimensional if I have an F, G, and H. So that's the difference between the two here. And this says where the components of F, G, and H are real-valued functions of the parameter t. Vector-valued functions are also written in the form ft(gt) or ft(gt)ht. And this is just that component form we're used to, or at least I am. Now below here, I'm dealing with a couple of two-dimensional vector-valued functions here. And we could tell because I just have an f and a g for both of these functions we're going to graph. So let's get started. So the first one I want to graph here is this number a. So I'm just going to pick some values for t. So I'm going to say t equals 0, t equals 1. So I just picked 4 values. So first off, I'm going to do t equals 0. So that just means I'm looking at R0, R0. And that means I'm just going to plug in 0 for t here. So the first one's going to give me 0 because 2 times 0 is 0. And this is going to be 0 plus 3 is 3. Now, honestly, this here is just some simple algebra for us to come up with these vectors here. So then where t equals 1, I'm going to get 2 comma 4. And where t equals 2, that's going to be 4 comma 5. And then for t equals 3, that's going to be 6 comma 6. Okay, so now we have some vectors to graph, and we're just going to graph those now. So for the first one, 0, 3. So 3 is there, so this vector is going to run straight up and there. That's going to be that first vector. Now the next vector is 2, 4. So 2, 4 is going to be there. So the vector is going to run this way. Now be careful not to overshoot the vector here. Make sure the very tip of it is at that point 2, 4. And then for 4, 5, it's going to be here. Oops, I'm going to fix that. Okay. And then the next one's going to be 6, 6. So that's here. So now drawing all these vectors, I'm going to try to straighten that one out a little more. There it is. That's better. Okay, we don't really care about the vectors themselves with these vector-valued functions. We honestly just care about the tips of those vectors. So right here, right on that point. So the way we can look at this is we can look at this as these vectors are like the pillars of a bridge in a sense, and we just really care about the line created from the heads of those vectors. So we get this line. So honestly, it's the line we care about here, not the vectors themselves. So just keep that in mind as you go through these. So we just did T0, T1, T2, T3. And this is when I talked about the lines a while ago in a video. That's what I was talking about there, that the vectors themselves don't matter. It's the points that are at the tips of each of those vectors that actually produce my path that we care about here. So this is what we end up with. And if we look at that line, we could probably come up with an equation for that line because we know the y-intercept, we know the slope, and we can see that the slope is rise over run. So up 1 to the right 2, okay? So we can see what's going on with that line. But just keep in mind with these vector-valued functions, every t that I plug in is going to give me a vector. But again, those vectors are not what matter here. It's just the tips of those vectors, the points resting on the top of each of those vectors that we care about. Okay, let's take a look at the next one now. So the sine of 3 sine t, 2 cos t. Now the values I'm going to pick here are 0, pi halves, and I'm just going to write those over here. So my t is going to equal 0, my t is going to equal pi halves, my t is going to equal pi, t is going to equal 3 pi halves, and then t is going to equal 2 pi. So then for my first vector, I'm plugging in 0 for t here. So the sine of 0 is 0. So I'm going to get 0 for my first one. And the cosine of 0 is 1. So that's going to be 2. 0, 2. Now the next one at pi halves, sine is actually 1 at pi halves. So that's going to be 3 times 1, which is 3. And then cosine at pi halves is 0, so it's 3, 0. And at pi, sine is 0 again. So I'm going to get 0 for the first one. And cosine is negative 1, which tells me this is now going to be negative 2. Now at t equals 3 pi halves, sine is negative 1. So negative 3. Fix my 3 there. Okay. And then cosine at 3 pi halves is actually 0. And then at 2 pi, sine is 0 again. And then cosine is going to be 1 times 2. So we get this 2. So we got 5 vectors to graph here. So that's what we're going to do now. So I just kind of scaled the graph there so we understand where we're coming from. So the first thing we're going to graph then is 0, 2. So 0, 2 is going to put me up here. So my vector is going to come this way, and it's going to be there. And then the next one is going to be 3, 0. So it's going to be this way. And it's going to be right there at 3, 0. These are kind of hard to see. Maybe what I'll do is I'll pick a different color. So I'll just redraw these. I figure green and red go well together. And then 0, negative 2, so that's going to be down here. And then negative 3, 0. That's going to be over here. Now the other thing to remember is remember your order we went in. And then 0, 2 again. That's going to take me back to here. Okay, so now all I'm going to do is graph those. Now remember here, we started here and we only care about the tips of those vectors. That's it. And that's why we can't overstep those with the vectors. And we started here and we're just going to kind of, and then we're going to keep going. And we're going to keep going. So we get this nice ellipse. And if you're not convinced that this ellipse is what we would get, we can always pick more vectors in between. So for instance, let's say I picked t equals pi fourths. Now I want to make sure I go in order, of course, so I want to make sure I put it before the pi halves. So just be aware of that too, because we have to go in order with our points as we get them, as t increases or decreases. So if I did this one, I'm just going to approximate it. This is probably 2.12 and then 1.41. And we'll just kind of keep it there. And then if you look at this here, so 2.12 is about there, and 1.41 is a little bit before that halfway mark there. So now if we just extended those out, so 2.12, it's going to put me about there. Then I do the same thing, 1.41, which is about there. We see that it's going to hit right there. Very nice. As you see, boom, there it is. So it would give us the vector, this here. And then again, remember, it's all about the point at the head of that vector. And you can see that it stays right on the path. So our direction also, we have a direction here. And we can see as t increases that our direction is going this way. So one thing that's kind of strange for these vector valued functions is that points are represented by a vector. So every vector is really representation of one point. There it is.